Better turn myself on. You all right? Excellent. A bit uncomfortable with wearing this wire. I have an Italian background. I can get killed for wearing a wire. But anyway, thank you everyone. I'm very happy to be here. I'm Gary Mancuso. I'm from Western Digital Corporation, along with the Data Center Systems Division. It's great to be here. We like getting in front of the HPC crowd because we know you guys are a huge consumer of storage. Disappointingly for us, though, it seems that all the attention is often on how many CPUs you have, how many GPUs you have, how large your cluster is, how big your compute infrastructure is, how many teraflops you can do, blah, 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 blah. Did we make the top 500, et cetera, et cetera. I'm thinking of starting my own top 500 and choose who has the most storage. Very happy to see. Look, there is a huge, obviously, interest in storage right now. Storage data, I should say, is the most important thing right now, which is what's powering the research. And without data, realistically, the compute doesn't mean much at all. So, Western Digital Corporation is now probably the largest storage company in the world, considering market cap and exabytes shipped as well. But definitely, because exabytes can be counted twice sometimes, definitely the broadness of our portfolio. So everything from the smallest flash chip for your embedded devices, USBs, SD cards, hard drives, home NAS, platforms for the enterprise, all sorts of devices for the enterprise, up to unified storage, shared storage arrays, and importantly, object storage now. We have an object storage system that scales to 63 terabytes and petabytes. Gee, I'm a storage guy. I better not get my terabytes and petabytes mixed up. 63 petabytes, that's very scale out. Now, I work for the Data Center Systems Division, as I mentioned, which is the red circle there. Those are the products that I concentrate on. And we are divided into devices, platforms, and systems. Sort of organisationally, I guess. So the products are logically divided. Like devices are straightforward, okay? Devices are hard drives and SSDs. We have all manner of hard drives and SSDs for different purposes. And platforms. So what's a platform then? For us, a platform is a chassis full of devices, okay? We just produce it like a JBOD. Instead of just supplying, and what we have done historically was just supply hard drives to the industry, we are now more and more providing finished products. So not just JBODs and JBOFs too, just a bunch of flash. We also do storage servers now as well. So what's a storage server? A storage server, therefore, is a platform, a chassis full of devices with compute added on, okay? And it's designed for you to take and build your own software-defined infrastructure, install whatever you wish upon it. Then our last division is systems. Systems are chassis with devices plus an operating system to make it work for you. Obviously compute in there as well. So we have two types of systems: the Agile, all flash and hybrid unified storage arrays, which you'll be hearing more about very soon, and not today, however, and our object storage systems. So Western Digital, we're about innovation, right? We, according to the IEEE, we have one of the most powerful patent portfolios in the world. Western Digital had a number of patents on its own right, but furthermore, in the last few years, Western Digital has made a couple of acquisitions, one being the SanDisk acquisition in 2016, which is how I came to join Western Digital, which brought upon the whole flash portfolio. 4 years before that, Western Digital had purchased HGST. And yes, HGST, people are asking, you Hitachi? No, we're not Hitachi. We bought Hitachi's old hard drive manufacturing subsidiary from them, which was called Hitachi Global Storage Technologies. Hitachi Global Storage Technologies in turn was formed between a merger of HGST's or Hitachi's hard drive making arm with IBM's hard drive making arm when IBM decided they didn't want to make components anymore either, and they sold their hard drive business. So what we effectively own there is the entire IP of hard drive history. This is Western Digital now, today. Furthermore, SanDisk, they were flash pioneers. One of the co-founders of SanDisk actually invented the floating gate transistor, which made flash possible. Toshiba was officially accredited with making the first flash chip. But ourselves and Toshiba, with Toshiba Memory Corporation, we're in a joint venture. We actually make our flash together and we share our technology. To that end, you know, we're now up to 96 layer 3D NAND. We're leading the industry there. A lot of the other manufacturers of flash actually license our technology from us. So we know a lot about flash. And I guess what I wanted to talk about next is we're working on the next generation of persistent memory, and we have been doing so for some years now. So the next generation of persistent memory, we are working on a form of memory called resistive RAM. So resistive RAM, basically the idea behind it is that by electrically altering the resistance value of the substrate of the silicon, by altering resistance, you alter the voltage. If you alter the voltage, you're effectively altering the value, and this is how we're going to derive the next generation of storage class memory. So we're currently testing. We anticipate, according to this timeline, that when we start, as you can see, we've already started producing 96 layer NAND. To continue to drive capacity and density in the current flash offerings. But we anticipate that resistive memory will be available at the end of this year, probably early next year. I mean, we've been testing it for some time. Some years ago, we were producing the chips, but at a kilobyte level. We anticipate that we're going to have much more greater density by the time we release this. So look out for the announcement. Like all new technologies, resistive RAM will probably be expensive to start with, but as we get production up and running more and more, it will come down in price. On the subject of price, I just wanted to talk quickly because I'm often asked by people, what are you guys doing to make SSDs cheaper? When will SSDs replace hard drives? It's not like we are trying to keep the prices of flash artificially high. We are manufacturing as much as we can. But there is a strong demand for it, and it's not just for the enterprise or HPC, it's the Internet of Things, all manner of smart devices, smart fridges, smart TVs, smartphones, smart watches, smart this, smart cars. All these things are taking some of our NAND chips, which then limits the supply for the enterprise as well. So we're trying to balance the supply or manage the demand, really. So the answer as to when will SSDs or when will flash memory replace hard drives is actually probably never. One reason is we can't manufacture enough of it just now to furnish existing demand. Secondly, I mean, if tape's not dead, I don't think we're going to cause the hard drives to be extinct anytime soon either. On the subject of tape, if you're saving data that probably doesn't need to be looked at for some time, or if you're saving it just for compliance sake, then by all means put it on tape. Our view, however, is that now, with more efficient helium drives, hard drives consume a lot less power, and if you do need that data from time to time, and when you do, you need it quickly for your researchers to do things, to retrieve data from some sort of past collection for analysis, then you're probably better off with object storage. We do have an independent TCO analysis that shows that our active scale object storage is more economical, a total cost analysis, a total cost of ownership analysis that shows it's more economical than LTO tape libraries. Additionally, one of the things we're looking at sort of in the background is the use of flash for long-term data storage. So flash might actually replace tape eventually, because if you look at flash, it's low power. You could write to flash and then put it away somewhere, okay? The thing is, people don't know this, but if you leave flash unattended for 4 or 5 years on a shelf somewhere, the floating gate might decay, its value might disappear. So we're looking at ways to run a maintenance current through flash to replace tape drives, right? So that's something for the future. It's something that came across recently. Don't know much about it yet, secret hush-hush stuff, so maybe I shouldn't be telling you. But in any case, to summarise, the point was that we can't make enough flash to cater for existing demand, and this is the projected future demand for data storage, right? So only recently did we hit a zettabyte, well, a few years ago, a zettabyte created. And the last few years we've been increasing by exabytes, but by 2025, if this is in fact turns out to be true, this projection means that we'll be hitting 163 zettabytes by 2025. And in order to do that by 2020 onwards, I mean, we're going to be growing by zettabytes, not exabytes anymore, right? So this is a huge amount of data growth that flash alone cannot provide the storage for. Therefore, we need hard drives, and furthermore, hard drives will probably still retain a cost per gigabyte advantage. So, on the subject of hard drives, Western Digital, continuing to innovate, we've just announced new technology called MAMR, Microwave Assisted Magnetic Recording, which should allow us to take hard drives to 35 to 40 terabytes. That would continue to keep the cost per gigabyte down, this increase in density. So hard drives are far from dead. We need them. Excuse me. So hard drives with lower power consumption with the helium drives, greater density, whatnot, they're starting to enter and intrude into tape territory, I think. In turn, flash is intruding into hard drive territory. And, but we'll need much more flash to be produced, and in turn, more persistent memory the next level up before we start to phase out anything, really. So producing flash is no mean effort, because it costs us about $1 billion to build the factory to start making it to start with. We currently have 7 fabrication plants through our joint venture with Toshiba Memory Corp. But if we eventually can produce large enough quantities of flash or persistent memory, and we can do it cheaply enough, then I think that it's not beyond the realms of possibility that one day we will be storing all our data on semiconductors, unless something else completely changes the ballgame. Because I've heard of a few different technologies that might catch some wind. So, furthermore, if resistive memory, or this much faster class of storage memory that's beyond flash, if we can build that to be fast enough, as fast as DRAM, while still being persistent, then we practically won't need all these tiers of storage. And I think that's decades away, okay? But it's possible to envisage that one day a computer will just be made up of a bank of memory that a CPU pokes data in and out of. And persistent memory, well, it might mean that one day memory is the computer. So, just for a second, I think I'll just introduce a new product of ours here, a new memory extension drive. So basically what this guy is a very high endurance, very fast NVMe SSD, designed to transparently expand your pool of DRAM, okay? So what it does and how it works essentially is that we present a virtual BIOS environment to the operating system where the total memory available is equal to your DRAM plus the capacity of this guy. It's available in a couple of different capacities, as you can see there, 1, 2, and 4 TBs. I apologise on behalf of the storage industry for introducing gigabytes and exabytes that aren't factors of 1024 times blah, right? And we cheated a little bit years ago because we were all racing to get to the terabyte first and whatnot. So you know the difference between megabytes and midis and etc. and whatnot. But anyway, that was a bit of an aside. So we present this one pool of memory to the operating system. However, whilst NVMe flash is fast, it's still not going to be quite as fast as your DRAM. So we do some intelligence behind the scenes. We actually use the DRAM as a cache. Okay, so we keep what is going to be, we think, very fancy algorithms here, we think that's going to be your more latency sensitive or frequently accessed bits, we leave them in DRAM. We stage in and out of the NVMe device. I have some test units, so you're more than welcome to do a POC. I'm happy to ship these things to you. Very easy to install for any in-memory application that you might have. So, onto platforms. I'm not going to talk too much about these because some of them are quite straightforward, but we have some new things here. So basically, we've introduced a new version of our JBODs with some new technology. We've also introduced the big brother, a 102-bay hard drive enclosure with SAS connections for your direct attach needs and distributed file system needs. Basically, the Data 102 allows you to have about 1.2 petabytes in 4 rack units. So increasing the density, great economics, because frankly, we manufacture the drives, don't forget, so how cheap do you want it, right? Also new, however, is our storage servers. So one key one to mention here is our, the hybrid storage server, so the UltraStar 60+8. We call it the 60+8 because it is effectively an extension of a JBOD with compute in it. Skylake CPUs, whatnot, available in 3 or 4 different configurations. There are 63.5-inch bays for hard drives, and there's also 8 2.5-inch bays for SSDs, dedicated for SSDs. So you can have a hybrid approach. You can also convert up to 24 of the 60 bays to 2.5-inch SSD as well. So you can have up to 36. 24 plus 8 is not 36, it's 32. 32 SSDs in this system. We also have flash storage servers. So this guy here is our NVMe server, 24 very fast NVMe devices out the front with a compute node in the back for whatever you want to do with it, basically. Then we also have a HA brother. So it is a dual controller system with a non-transparent PCI bridge in between the two. Has a number of applications, and I will talk about a couple in a minute, perhaps, if I have time. And lastly, this is relatively very brand new, this guy. The Serve24A is a very hardened, transportable. I have 10 minutes. Thank you. This is designed for in-the-field data ingest, collecting data, research data in the field perhaps. Also, people want to get maybe data to the cloud or whatnot. It's getting difficult to ship all those petabytes over the network, so you can store it on this and carry it to your AWS office if you wish. Okay, I will move on. So this is E8 Storage. You may have heard of this company. There's also another company I'll talk about in a minute called Accelero. Both these guys, in effect, sort of partner with us. We like innovation, so Western Digital has actually invested in both these companies. These guys do scale out, RAID, NVMe type software-defined storage. So you take an NVMe server, you create LUNs on it, present to your application tier. They do certain things really well. They do things very similar, but they're also different in certain instances. E8 has actually productized our HA storage server, and on their bezel they put their powered by Western Digital, which is kind of nice of them. Accelero is the other one. I can organise POCs or technical presentations from tech reps of both these companies. I think what they do is quite interesting, quite good. They have differences, as I said. Contact me if you want more information. I'm not going to talk too much about these guys just now. If you've got questions, see me offline. I'm going to move on to what I really wanted to talk about today. The rest is just the intro. I might stop for questions at this point. Does anyone have any questions I'd like to ask about anything storage related, of course?
Please. Was that a PCIe interconnect or a connector for your UltraStore memory, additional memory?
The memory extension device?
Memory extension device.
It's a PCIe device, yes. That is an NVMe SSD, yes.
Okay.
Yes. Okay, so on to what's brand new and our latest innovation. It's a product called OpenFlex, and I'd like to talk a bit about software composable infrastructure, or open composable infrastructure. So, what we've been seeing a little bit of is a shift from SAN to direct attached. There's various reasons for that. Some SANs provide certain features better than others. Some SANs provide very good features that you still can't do without. But more and more, some of these features are being furnished by software. Okay, operating system, distributed file system. There's all manner of smart layers in further up the stack. where maybe you don't need SAN all the time, right? Particularly in a distributed file system, you just need DAS attached everywhere, and other things such as redundancy and things are created elsewhere. Also, NVMe flash in particular can be too fast for SAN because it is so fast that having a controller or the SAN controller in front of it and your application might not be conducive to having the best latency. Particularly when SANs might have a mixture of different tiers of storage, the controller can get held up on drives or slower SATA SSDs if they're also attached to the same system to which these NVMe drives are attached. So the NVMe drive might respond quickly to the storage controller, but the storage controller is bogged down doing other things and won't respond to your application tier. So for that, DAS has become popular, especially with fast flash and PCIe flash. You install it directly into your server and it's much faster. You're closer to the CPU where the work is being done. Which leads us to the third evolution now, which is this is an evolution that we're seeing. We're moving to NVMe over Fabric. Okay, so with NVMe over Fabric, you've got an RDMA network, which is now practically giving you the best of both worlds, because it combines the low latency of direct attached with the flexibility of SAN, because you can attach it to anywhere in your infrastructure, basically. Keep that in mind. So what do I mean by composable infrastructure? Well, software composable infrastructure. What we're talking about is breaking the bounds of the chassis. I mean, this is not new, this concept, right? It's about no longer being confined within tin, okay? You've all heard of orchestration, OpenStack. It's sort of a similar thing where you're virtualizing your entire infrastructure. You're not just virtualizing a server into multiple servers. You can now take practically, what we're envisioning is you take CPU from anywhere in your infrastructure, you can map it to network anywhere in your infrastructure and connect it to devices anywhere in your infrastructure. Like your infrastructure should look like a matrix. Everything interconnected and easily, flexibly attached or detached as you're required. So you can compose virtual systems from everything. So what we intend with this is to create storage devices which are network connected directly. Core elements that are network connected in your infrastructure, and they no longer have to be slaves or subcomponents, because storage always had to be attached to a compute node to then be shared and whatnot. So these are going to be shared directly connectable over the fabric. So our vision for SCI is that it be open, scalable, disaggregated, not siloed, and therefore flexible and universal. So to that end, what we've done is we've created this new API, open API. We intended for it to be open. We're collaborating with many vendors on this. The API is called Kingfish. It's like an extension or a superset of Redfish, which you may have, has everyone heard of Redfish before? You know what Redfish is, yeah? So it's basically like an API for managing platforms, you know, lights out management and stuff. With what we use for our platforms, it's really starting to become mainstream, and our storage servers also. Then there's another one called Swordfish, which is what the traditional storage vendors are doing for logical volume management support. So this is a superset though. This is Kingfish, where anything we feel, or we hope, will eventually be able to be accessed by this API and orchestrated into this composable infrastructure. We have made a management plugin for OpenStack to demonstrate how it works, and so we're hoping that it will garner broader industry support, and everyone will have a way to plug into this API. So to that end, these are our main announcements today. I guess this is what's new, data infrastructure. These are new fabric devices, if you will, storage fabric devices, shall we call them that for now. These are two new platforms. One's called the E3000 and one's called the D3000. The E3000 is flash-based, and the D3000, interestingly, for the first time ever, is actually a pool of hard drives, which you'll be able to access over NVMe over Fabric. So in other words, RDMA for hard drives now, right? Let's examine the E3000 first. I'll talk about this quickly. The best way to look at it is that it's a JBOD, right? But it's as opposed to a traditional JBOD, which is SAS or fiber channel connected to a host, this guy is network connected directly into infrastructure. It's an enclosure that contains 10 discrete flash modules, and as you can see from the back of this device, there are 20 QSFP connections, 50 gigabit for your network connections. And this is the flash module that plugs into it. So the E3000 can hold 10 of these. And each one of these is a very smart SSD device with, up to, we can have 2 options, 1 drive write per day or 3 drive writes per day. With 2 50 gigabit Ethernet ports on each one. And they plug into the E3000 chassis, basically. The capacity is optional, okay, so it ranges in the 1 drive write per day from 15 to 60 terabytes each. Well, the 3 drive write per day, slightly less capacity, because as you know, over provisioning is what helps us with the endurance. 12.8 or 25 terabytes. Therefore, a full E3000 could theoretically hold 600 terabytes of raw flash in 3 rack units, directly connectable via high-speed internet, Ethernet, to your infrastructure. So there's potentials for lots of use cases here, high-performance scratch space perhaps. So this is the D3000, as I mentioned just now, for the first time ever, a pool of drives, a pool of hard disks, accessible over an RDMA fabric. So it's 168 terabytes in 1 RU, which is presented as one pool. Inside, I'm not sure of the hardware details because this is a very new announcement. I haven't actually seen the hardware yet, but I believe that in the inside it's made up of 14 terabyte SMR drives for cost effectiveness, plus fronted by some flash, and the flash acts as a cache, so that way it sequentializes the writes for optimum SMR performance. Whilst we've just announced it, we're talking about Ethernet a lot, InfiniBand will also be supported. So, on that end, I was going to conclude with maybe a little bit of a talk about NVMe, if people are interested, but welcome to what we foresee as being a new world of fabric-connected all sorts of devices. What's driven this, I guess, is it started just simply with the development of NVMe. And while NVMe stands for Non-Volatile Memory Express, it was built upon PCI. There were dual aims with NVMe. When we go back to the first ever flash PCI devices, which was technology pioneered by Fusion.io, a company that you might have heard of in the past, who was subsequently acquired by SanDisk. These products were basically SSDs on PCIe cards. You installed them directly into your PCIe bus. That brought them much closer to the CPU. Excuse me. And that was for latency. It gave you much better latency. Bringing them closer to the CPU makes it much faster. But the issue is, to make these devices work is Fusion.io gave you a driver. When other companies started making their own flash PCIe devices, everyone had a driver. Okay. Now I like drivers sometimes, because if you want to add a new feature, you just update the driver and install it and you've got new features. If it's hardware, you have to upgrade your hardware to get new features, right? But nevertheless, they simplified it, because by producing this NVMe interface, it meant that you didn't need different drivers for every NVMe device. It's a standard, so any NVMe device will plug into and work on anything that supports NVMe. But people don't understand that there was a secondary aim with NVMe. One of the problems that Fusion.io solved, for example, is I've got a system with latency. Let me install a PCIe flash card. That'll make it faster. That was good, and it did that. The trouble is, to put it in, you had to open up the box, take downtime, stick the card in, okay? So the concept of NVMe was not just to standardize the drivers, it was also to bring the PCIe bus out to the front of the server, so it was hot pluggable. So you could now hot plug a PCIe hard drive, flash drive. And so what NVMe over Fabric is now doing is extending, like NVMe extended the PCIe bus to the front of the server, NVMe over Fabric is now extending the PCIe bus beyond the server. And on that I'm going to conclude. Does anyone have any questions? Cool. Thank you, everyone.